The solar system looks simple from a distance, but every world within it has a story shaped by extreme heat, frozen landscapes, violent impacts, and billions of years of change. The planets we see as small lights in the sky are far more complex than they appear, and each one holds clues about how our cosmic neighborhood formed and evolved. In this series, we break down those worlds one by one, from scorched Mercury to storm-filled Jupiter, from Mars's ancient rivers to Venus's runaway greenhouse. The edge of Earth. The edge of Earth is not marked by a wall, a visible border, or a sudden break. It is a gradual transition where air becomes thinner, gravity weakens slightly, and the blue sky slowly fades into the blackness of space. This boundary, often imagined as a sharp divide, is actually a complex region shaped by physics, radiation, temperature extremes, and the fragile layers of Earth's atmosphere that make life possible. Humanity has always looked upward and wondered where Earth truly ends. For thousands of years, the sky appeared endless. Only in the last century did we begin to understand that our planet is wrapped in delicate atmospheric layers that extend far beyond what the human eye can see. As we rise above the surface of Earth, the first major region we enter is the troposphere, the layer where all weather occurs. This is where clouds form, winds blow, and storms develop. Nearly all life on Earth exists within this thin shell of air that reaches only about 12 kilometers above sea level. Compared to the size of the planet, this layer is thinner than the skin of an apple. Above the troposphere lies the stratosphere, a calmer region where commercial aircraft fly and where the ozone layer absorbs most of the sun's harmful ultraviolet radiation. Without this protective shield, life on the surface would not be possible. Temperatures here stop dropping and begin to rise again as sunlight interacts with ozone molecules. Beyond the stratosphere, the atmosphere continues into higher and thinner layers, known as the mesosphere, thermosphere, and finally, the exosphere. With each layer, the air becomes more rarefied, temperatures behave in extreme ways, and the influence of space becomes more dominant than the influence of Earth. At around 80 to 100 kilometers above sea level lies what is commonly called the boundary of space, known as the Kármán line. This is the altitude where the atmosphere becomes too thin to support conventional aircraft flight. Beyond this point, aerodynamic lift no longer works, and spacecraft must rely entirely on orbital mechanics to remain aloft. Crossing this boundary does not feel dramatic in a physical sense. There is no explosion of silence, no visible wall, no sudden disappearance of Earth's pull. Yet everything changes here. Above the Kármán line, the sky is no longer blue. It becomes completely black, even during daytime. The curvature of the Earth becomes clearly visible, and the fragile shell of atmosphere reveals itself as a faint, glowing layer hugging the surface. This fragile layer is all that protects life from the vacuum of space, cosmic radiation, and extreme temperature swings that range from hundreds of degrees below zero to hundreds of degrees above. Orbiting above this boundary is the International Space Station, traveling at nearly 28,000 kilometers per hour. From this vantage point, astronauts witness 16 sunrises and sunsets every single day. From this altitude, Earth appears peaceful and complete, yet visibly fragile. There are no borders, no nations, only oceans, land, clouds, and a thin blue atmosphere, separating living world from dead vacuum. The edge of Earth is not only a physical boundary, but also a technological one. Every spacecraft that has ever left the planet must pass through this narrow corridor between sky and space. Rockets pass through extreme aerodynamic stress as they accelerate through the dense lower atmosphere before breaking free into orbit. A failure at this stage is often catastrophic, which is why launch remains one of the most dangerous parts of space travel. Above the atmosphere, gravity still dominates. Even though astronauts experience weightlessness, they are not truly beyond Earth's gravitational pull. They are actually in a continuous state of falling around the planet, moving so fast sideways that they keep missing the surface. This balance between speed and gravity is what creates orbit. From this region above Earth, the planet's true shape becomes undeniable. The horizon curves sharply. Continents drift past beneath blankets of cloud. At night, city lights trace patterns across the surface, revealing the footprint of civilization on a planetary scale. But beyond low Earth orbit, conditions grow far harsher. The remaining traces of atmosphere vanish almost entirely. Radiation from the sun and distant cosmic sources becomes a far greater threat. Without Earth's magnetic field to shield them, astronauts and electronics are exposed to particles moving at nearly the speed of light. This thin magnetic shield, known as the magnetosphere, extends far beyond the visible atmosphere and deflects much of the solar wind. Without it, Earth's atmosphere itself would slowly be stripped away, as happened long ago on Mars. The edge of Earth is also where temperature stops behaving in ways that feel familiar. In the vacuum of space, heat does not move through air. Objects facing direct sunlight become extremely hot, while objects in shadow plunge into deep cold. This creates thermal stress that spacecraft must be engineered to survive for years at a time. Every mission that has ever traveled beyond Earth begins here, at this boundary. From early satellites to modern space stations, from lunar missions to interplanetary probes, all pass silently through this invisible gateway. The first human to experience this transition was Yuri Gagarin in 1961. As he orbited Earth, he crossed this invisible boundary repeatedly, proving for the first time that a human being could survive beyond the protective cocoon of the planet's atmosphere. Since then, hundreds of astronauts have followed. Yet even today, for nearly all of humanity, the edge of Earth remains unreachable. It is visible only through cameras, calculations, and the experiences of a few travelers who have crossed it. The edge of Earth is not just a place of altitude. It is the final point where Earth's influence is stronger than space itself. Beyond this region, the laws that govern daily human life gradually give way to the deeper laws of the universe. It is here that sound disappears. It is here that fire cannot burn. It is here that even basic human survival becomes impossible without layers of engineering and constant life support. And yet, despite these dangers, this boundary is where every journey to the stars must begin. From this thin border between sky and void, humanity looks outward toward the moon, toward the planets, and toward the distant stars. Everything beyond this point belongs not to Earth, but to the universe itself. The edge of Earth is not the end of our world. It is the place where our world opens into something far larger. And from here, every deep space journey truly begins. What is a light year? One of the greatest challenges in understanding the universe is not size, temperature, or energy, but distance. Space is not measured in kilometers or miles in any practical sense once we leave the neighborhood of Earth. The scale becomes so vast that ordinary units lose meaning. To solve this problem, astronomers rely on a unit that seems simple in name but overwhelming in reality: the light year. A light year is not a measure of time, despite what the word suggests. It is a measure of distance. Specifically, it is the distance that light travels in 1 year through the vacuum of space. Light moves at roughly 300,000 kilometers per second. Over the course of 1 year, that adds up to approximately 9.46 trillion kilometers, or nearly 5.88 trillion miles. That single number already exceeds all everyday human scales of travel. To place this in perspective, the moon is about 384,000 kilometers away from Earth. Light takes just over 1 second to reach it. The sun, which appears close in the sky, is about 150 million kilometers away. Light takes just over 8 minutes to reach Earth from the sun. Even within our own solar system, light time becomes measurable in minutes and hours. But once we step beyond our solar system, the scale changes completely. The nearest star system to Earth is Alpha Centauri, located about 424 light-years away. This means the light we see today from that system left those stars more than 4 years ago. In other words, we are always looking into the past when we observe distant stars. The farther away an object is, the older the light becomes by the time it reaches us. This effect is not a theory or illusion. It is a direct and unavoidable consequence of the finite speed of light. Inside the Alpha Centauri system is a small red dwarf star called Proxima Centauri, which is slightly closer at about 4.24 light-years This star hosts at least one known planet, Proxima b, which orbits within the habitable zone. Even at this closest possible neighboring distance in cosmic terms, reaching such a star using current technology would require tens of thousands of years. To understand why this is the case, it helps to compare light with the fastest objects humanity has ever built. One of the fastest spacecraft ever launched is Voyager 1, which is currently traveling at roughly 61,000 kilometers per hour relative to the Sun. At this speed, Voyager 1 would take more than 70,000 years to reach Proxima Centauri. This comparison alone shows how far light speed travel remains from our technological reality. The concept of a light year allows astronomers to describe distances that would otherwise require huge numbers filled with zeros. For example, the diameter of our own galaxy, the Milky Way, is about 100,000 light years across. This means that light emitted from one edge of the galaxy takes 100,000 years to reach the other side. When we observe distant regions of our galaxy, we are seeing them, not as they exist today, but as they existed tens of thousands of years in the past. When we look beyond our galaxy, distances increase even more dramatically. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. The light we see from Andromeda today began its journey toward Earth before the first human ancestors ever walked upright. The deeper astronomers observe into space, the farther back in time they see. At extreme distances, telescopes observe light that began its journey shortly after the Big Bang itself. This connection between distance and time is one of the most important but least intuitive ideas in all of astronomy. Space does not simply show us where things are, it shows us when they were. Every point of light in the sky represents a different moment in cosmic history, layered across time by distance. Light years are not only used to measure distances between stars and galaxies, they also define the limits of observation itself. There exists a boundary, known as the observable universe, which represents the farthest distance from which light has had enough time to reach Earth since the beginning of cosmic expansion. This boundary lies about 46 billion light years away in all directions. Beyond it, there may be more universe, but its light has not yet had enough time to arrive. For human exploration, even distances within a single light year present challenges far beyond our current capabilities. Chemical rockets, which power the Apollo missions and modern spaceflight, can only achieve a tiny fraction of the speed of light. Even advanced ion engines, which are extremely efficient for long-duration missions, still move at speeds that are minute compared to cosmic distances. To reach another star system within a human lifetime using conventional propulsion would require velocities approaching at least 10% of the speed of light. At that speed, a journey to Proxima Centauri would still take more than 40 years, not including time needed for deceleration, course correction, and arrival operations. This is why the measurement of light years is not merely a scientific convenience, but a direct representation of the limits imposed on physical travel by the laws of nature. Every light year marks a region of space where communication, exploration, and survival face increasing technological and biological challenges. Even communication across light-year distances is delayed by the speed of light. If a signal were sent today to a spacecraft orbiting a planet around Proxima Centauri, it would take over 4 years to arrive. A reply would take another 4 years to return. Every conversation across such distances would unfold across decades. The light year also shapes how we define cosmic neighborhoods. The stars visible to the naked eye all lie within a few thousand light years of Earth. The bright band of the Milky Way we see in the night sky represents the dense inner disk of our galaxy, stretching across tens of thousands of light years. Beyond that lie billions of other galaxies, each separated by millions or billions of light years. From this perspective, even entire civilizations could rise and fall between the moment a beam of light leaves a distant world and the moment it finally reaches Earth. The universe we observe is therefore not a snapshot of a single moment, but a layered archive of cosmic history spread across unimaginable distances. Understanding the light year is fundamental to understanding why interstellar travel remains one of the greatest technological challenges humanity has ever faced. It is not merely about building faster engines, it is about confronting distances so large that they reshape how time itself is experienced. Every exploration mission we have ever launched remains confined to a tiny bubble surrounding Earth when measured in light years. Even Voyager 1, the most distant human-made object, is still less than 1,000th of a single light year away from our planet. This means that all of human spaceflight history, so far, has taken place within an almost invisible fraction of interstellar space. Yet the light year does more than define limitations. It also shows what is possible in principle. Light itself crosses these vast distances constantly, carrying information from stars, planets, and galaxies to our telescopes. Through light alone, we have learned the composition of distant stars, the atmospheres of alien worlds, the birthplaces of galaxies, and the expansion of the universe. In this way, the light year becomes not only a measure of separation, but a bridge of information connecting Earth to the rest of the cosmos. It allows humanity to explore without traveling, to observe without crossing physically, and to understand without touching. As our technology advances, future generations may one day cross distances measured in light years, rather than kilometers. Until that time arrives, the light year remains the unit that defines the scale of ambition itself. It marks the boundary between what humanity has already explored and what still lies far beyond reach. The speed of light. The speed of light is the single most important constant in the universe. It is not just the speed at which light travels. It is the maximum speed at which information, energy, and cause and effect itself can move through space. Every process in the universe is shaped by this limit. Nothing with mass can reach or exceed it, and nothing that happens anywhere can be known faster than light allows. In a vacuum, light travels at approximately 299,792 kilometers per second, or about 186,182 miles per second. This number is so large that it is difficult to compare to any ordinary experience. In one single second, light can travel around the entire Earth more than 7 times. In 8 minutes, it crosses the distance between the Sun and Earth. In 1 year, it travels nearly 10 trillion kilometers, forming the basis of the unit known as the light year. The speed of light is not just an observed value. It is a fundamental property of reality. According to modern physics, it is woven into the structure of space and time themselves. This understanding was transformed forever in the early 20th century through the work of Albert Einstein, whose theory of relativity revealed that space and time are not separate backgrounds of the universe, but are interconnected aspects of a single structure called space-time. One of the central conclusions of relativity is that the speed of light is the same for all observers, regardless of how fast they themselves are moving. This idea may seem abstract, but its consequences are profound. It means that time itself can slow down, and distances can contract for objects moving at high speeds. The faster an object moves through space, the more slowly it moves through time. At everyday speeds, these effects are far too small to notice. But as speeds approach a significant fraction of the speed of light, the effects become dramatic. A spacecraft traveling at half the speed of light would experience noticeable time dilation, meaning time on board would pass more slowly than time on Earth. At 90% of the speed of light, time slows dramatically. At the speed of light itself, time would effectively stop entirely from the perspective of the moving object. This is one of the reasons why objects with mass can never reach the speed of light. Doing so would require infinite energy. The speed of light is therefore not just a high speed, it is a boundary embedded into the laws of physics. It limits how fast particles can move, how quickly forces can act, and how rapidly the universe itself can change. This limit shapes the structure of the cosmos on every scale. It defines how quickly stars can be influenced by one another, how fast galaxies can interact, and how rapidly the expanding universe can evolve. Even gravity itself is limited by the speed of light. Changes in a gravitational field do not travel instantly. They propagate at light speed as gravitational waves. Because light does not travel infinitely fast, there is a delay between events and their observation. When we see the sun as it appears in the sky, we are seeing it as it was 8 minutes ago. When we observe distant stars, we are seeing them as they existed years, centuries, or thousands of years in the past. When we observe distant galaxies, we are observing light that began its journey millions or even billions of years ago. This delay turns astronomy into a form of time travel. Telescopes do not simply look outward in space, they also look backward in time. The farther away an object is, the further into the past its light originated. At the largest observable distances, astronomers see the universe as it existed shortly after its beginning. The speed of light also defines the maximum size of the observable universe. Even though space itself may be far larger than what we can see, light from the most distant regions has not yet had enough time to reach us since the beginning of cosmic expansion. As a result, the observable universe appears as a vast sphere of space centered on Earth, bounded not by physical walls, but by the finite age of the universe and the finite speed of light. From a technological perspective, the speed of light represents the greatest barrier to interstellar and intergalactic travel. Even the fastest spacecraft ever built move at speeds that are tiny fractions of light speed. The Parker Solar Probe holds the current record as the fastest human-made object, reaching speeds of over 690,000 kilometers per hour near the Sun. While this is astonishing by engineering standards, it still represents less than 0.1% of the speed of light. At this speed, reaching even the nearest star system would take thousands of years. This gap between human engineering speeds and the cosmic speed limit illustrates just how far present-day technology remains from enabling true interstellar travel within a human lifetime. The ultimate reason for this limitation lies in the relationship between energy and mass. As an object accelerates and approaches the speed of light, its effective mass increases, requiring ever greater amounts of energy to continue accelerating. Near light speed, even the output of entire stars would be insufficient to push a massive spacecraft the final fraction of the way to light speed. This creates a natural barrier that cannot be overcome by brute force alone. Despite this, scientists continue to explore how close objects can theoretically approach this fundamental limit. Concepts such as antimatter propulsion, advanced fusion engines, and photon-based propulsion systems are all attempts to reach a meaningful fraction of light speed. Even reaching 10 or 20% of light speed would represent a revolutionary change in space exploration, reducing interstellar travel times from tens of thousands of years to a matter of decades. The speed of light also governs how information moves through the universe. No signal can travel faster than light. This means that instantaneous communication across vast distances is physically impossible. A message sent to a spacecraft near the orbit of Jupiter takes more than 30 minutes to arrive. A message sent to a spacecraft near the nearest star would take over 4 years. Any reply would require another 4 years to return. This delay would fundamentally reshape human exploration of deep space. Interstellar missions would require a high degree of autonomy, artificial intelligence, and long-term self-reliance because real-time control from Earth would be impossible. The speed of light further defines how cause and effect are linked in the universe. An event cannot influence another event if there is not enough time for light or information to travel between them. This creates a web of causality that structures everything from atomic interactions to the evolution of galaxies. Even the behavior of subatomic particles is shaped by this limit. In particle accelerators, scientists routinely accelerate particles to speeds extremely close to that of light. As they approach this limit, their energy increases dramatically, while their speed increases only slightly. This behavior confirms the predictions of relativity with extraordinary precision. At the extreme edge of physics, the speed of light also sets boundaries on what we currently understand about space and time. Inside black holes, gravity becomes so intense that not even light can escape. This is why black holes appear dark, not because nothing is happening inside them, but because nothing that happens inside can influence the outside universe once it passes the event horizon. In this way, the speed of light separates visible reality from hidden regions of the universe that may forever remain beyond direct observation. It draws a line between what can be seen and what must remain unknown. Despite being a limit, the speed of light is also what makes the universe visible at all. Without it, there would be no flow of information across space. Stars would burn unseen. Galaxies would form in silence. The universe would exist, but it could never be observed. Every image captured by telescopes, every signal received by antennas, and every measurement of distant cosmic events depends entirely on light carrying information across vast distances at this fixed and constant speed. The speed of light therefore connects the smallest scales of physics with the largest scales of cosmology. It links atoms to galaxies, seconds to billions of years, and local experiments to the structure of the universe itself. For humanity, it defines both our greatest obstacle and our greatest window outward. It limits how far we can travel within a lifetime, and at the same time it allows us to see farther than any physical journey could yet take us. Our silent neighbor, the moon. The moon is the closest celestial body to Earth and the only other world that human beings have ever visited. It appears calm, distant, and unchanged. Yet its presence has shaped the history of our planet more deeply than almost any other object in the sky. From ocean tides to the stability of Earth's climate, from ancient calendars to the birth of space exploration, the moon has quietly influenced life for billions of years. The moon orbits Earth at an average distance of about 384,000 kilometers. At this distance, it takes light just over 1 second to travel from the moon to Earth. In cosmic terms, this is extremely close. Within this narrow gap between the two worlds, a powerful gravitational relationship exists, binding Earth and the moon together in a slow and stable dance that has lasted for more than 4 billion years. Scientists believe the moon formed shortly after Earth itself, following a massive collision between the young Earth and a Mars-sized object in the early solar system. This event is known as the giant impact hypothesis. The collision ejected vast amounts of molten material into space, which gradually came together under gravity to form the moon. The evidence for this violent birth can still be found in the chemical similarities between Earth's mantle and lunar rocks. Once formed, the moon immediately began shaping Earth in ways that continue to this day. One of the most powerful effects is the creation of ocean tides. The moon's gravity pulls on Earth's oceans, causing regular rising and falling of sea levels across the planet. These tides influence marine ecosystems, coastal erosion, and even the long-term movement of Earth's crust. Without the moon, Earth would experience much weaker tides driven mainly by the sun. The moon also plays a crucial role in stabilizing Earth's rotation. Earth is tilted at an angle of about 23.5 degrees relative to its orbit around the sun. This tilt is responsible for the changing seasons. The gravitational pull of the moon helps keep this tilt remarkably stable over long periods of time. Without the moon, Earth's axis could wobble chaotically, leading to extreme and unpredictable climate changes that would make the development of complex life far more difficult. Although the moon appears constant in the sky, it is slowly moving away from Earth. Measurements using laser reflectors left on the lunar surface by astronauts show that the moon is drifting away at a rate of about 3.8 centimeters per year. Over hundreds of millions of years, this gradual separation will continue, slowly altering Earth's tides and rotational behavior. The surface of the moon tells a story of violent ancient impacts and geological stillness. Unlike Earth, the moon has no thick atmosphere to burn up incoming meteoroids and no active plate tectonics to reshape its surface. As a result, most impact craters remain preserved for billions of years. These craters record the history of bombardment in the early solar system and provide scientists with direct evidence of ancient cosmic collisions. Large dark regions visible on the moon are known as lunar maria. These basaltic plains formed when ancient volcanic eruptions filled massive impact basins with molten rock. Despite these ancient volcanic features, the moon today is geologically quiet. There is no active volcanism, no flowing water, and no weather to reshape the landscape. Time on the moon moves extremely slowly compared to Earth. For most of human history, the moon was observed only with the naked eye and later through early telescopes. It guided calendars, inspired myths, and shaped early navigation. Yet it remained physically unreachable until the mid-20th century, when spaceflight became possible. In 1969, humanity reached the moon for the first time during the Apollo program. The mission Apollo 11 carried astronauts Neil Armstrong and Buzz Aldrin to the lunar surface. Their landing marked one of the most significant technological achievements in human history. For the first time, a species born on one world successfully traveled to another. During the Apollo missions, astronauts collected hundreds of kilograms of lunar rock and soil, installed scientific instruments, and conducted experiments that revolutionized our understanding of both the moon and Earth. These samples revealed that the moon contains no significant atmosphere, no liquid water on the surface, and a composition closely related to Earth's mantle. The Apollo missions also left behind retroreflectors that are still used today to measure the distance between Earth and the moon with extreme precision. These measurements confirm that the moon is slowly drifting away, and that Earth's rotation is gradually slowing as a result of tidal friction. Although the Apollo era ended in the early 1970s, the moon never lost its importance. Robotic missions from many countries have continued to explore its surface, orbit, and hidden regions. One of the most significant modern discoveries is the presence of water ice in permanently shadowed craters near the moon's poles. These craters never receive direct sunlight, allowing ice to remain frozen for billions of years. The discovery of lunar ice has transformed views of the moon from a dead world into a potential gateway for future exploration. Water can be used not only for drinking, but also for producing oxygen and rocket fuel. This makes the moon an important stepping stone for long-term missions to Mars and beyond. Today, new missions aim to return humans to the moon with long-term presence rather than brief visits. Programs like NASA Artemis program seek to establish sustainable lunar operations and prepare the technologies required for deep space exploration. The moon's low gravity, lack of thick atmosphere, and proximity to Earth make it an ideal testing ground for future interplanetary missions. Technologies for habitat, construction, life support, radiation protection, and long-duration survival can be tested on the moon before they are used on far more dangerous journeys. Beyond science and exploration, the moon also serves as a natural record of the early solar system. Because its surface has remained largely unchanged for billions of years, it preserves evidence of the violent period when planets were forming, and impacts were far more frequent than they are today. By studying lunar craters, scientists learn about the history of impacts that once shaped all the inner planets, including Earth. The moon also plays an important role in protecting Earth. Its gravity helps deflect some incoming asteroids and comets that might otherwise collide with our planet. While it is not a shield in the traditional sense, its presence alters the gravitational environment of near-Earth space in subtle but meaningful ways. Despite being lifeless on the surface, the moon continues to influence the rhythms of life on Earth. Many organisms still respond to lunar cycles. Tidal patterns driven by the moon affect coral spawning, fish migration, and coastal ecosystems. Even human culture remains tied to the moon through calendars, language, and symbolism. From the edge of Earth, the moon is the first destination beyond our planet and the last place where humanity has left physical footprints on another world. It remains both a reminder of past exploration and a promise of future journeys. The moon is silent, airless, and frozen in time, yet its influence is constant and powerful. It has shaped Earth's oceans, stabilized its climate, guided human clocks, and ignited humanity's desire to travel beyond its homeworld. As humanity prepares for deeper missions into the solar system and eventually toward other stars, the moon will remain our closest training ground and our most familiar companion in the darkness of space. The solar system in scale. The solar system often feels familiar because its main members are taught in classrooms, printed on posters, and modeled on small desk displays. The Sun at the center. The 8 major planets moving in stable paths. a handful of moons, belts of rocks, and distant icy objects. On paper, everything appears orderly and compact. In reality, the solar system is so vast that nearly all human intuition about distance completely fails. At the center of the system lies the Sun, a star containing more than 99% of all the mass in the solar system. Everything else, planets, moons, asteroids, comets, and dust, together make up less than 1% of the total mass. This massive imbalance is the reason the Sun controls the motion of every object around it through gravity. The average distance between Earth and the Sun is defined as 1 astronomical unit, abbreviated as 1 AU. This distance is about 150 million kilometers. Even this single unit is already far beyond direct human experience. Light takes just over 8 minutes to cross this distance. At the speed of a modern jet aircraft, the same journey would take more than 18 years. When scaled accurately, the solar system immediately becomes difficult to visualize. If the Sun were reduced to the size of a grapefruit, Earth would be a tiny grain of sand orbiting about 15 meters away. The Moon would be another smaller grain of sand orbiting Earth at less than half a meter. Mercury and Venus would be placed closer to the Sun within a few meters. Mars would orbit farther out at more than 20 meters. Jupiter, the largest planet, would be a small marble more than 80 meters away. Saturn would be even farther. Uranus and Neptune would be placed hundreds of meters from the Sun. Pluto, now classified as a dwarf planet, would orbit several kilometers away in the same scale model. This simple scaling reveals the first major truth of the solar system. The planets are separated by enormous empty spaces. The solar system is not crowded. It is mostly vacuum. Even the inner solar system, where all rocky planets reside, is dominated by empty distance. Mercury, Venus, Earth, and Mars appear tightly grouped in diagrams, but in reality, the gaps between them are vast. Spacecraft traveling between these worlds spend almost all of their journey moving through empty interplanetary space. Beyond the orbit of Mars lies the main asteroid belt, a wide region filled with millions of rocky fragments. Despite popular fiction, this region is not tightly packed with collisions. The average spacing between asteroids is so large that a spacecraft could pass safely through the belt without striking anything. The belt exists as a broad disk of scattered debris, rather than a dense field of rocks. Past the asteroid belt lies the domain of the gas giants. Jupiter dominates this region with more mass than all other planets combined. Its powerful gravity shapes the orbits of countless asteroids and comets. Jupiter alone demonstrates the scale of planetary size compared to Earth. Its diameter is more than 11 times that of Earth, and more than 1,000 Earths could fit inside its volume. Yet even Jupiter, massive as it is, occupies a tiny region of space compared to the distances between planets. From the orbit of Jupiter, the Sun appears 5 times smaller in the sky than it does from Earth. Light now takes over 40 minutes to travel from the Sun to Jupiter. Beyond Jupiter lies Saturn, followed by the ice giants Uranus and Neptune. The distances between these outer planets expand dramatically. A spacecraft traveling between Saturn and Uranus must cross billions of kilometers of empty space. By the time one reaches Neptune, the Sun is no brighter than an unusually bright star. At Neptune's orbit, light requires more than 4 hours to reach the planet from the Sun. Communication signals to robotic spacecraft take equally long to arrive. Every command sent from Earth must travel across this immense void before reaching its destination. Any reply then takes just as long to return. Even within our own solar system, communication delays become operational challenges. For a long time, Neptune was considered the edge of the planetary system, but beyond it lies an even larger domain known as the Kuiper Belt. This region contains icy objects, dwarf planets, and remnants left over from the formation of the solar system. One of the most famous members of this region is Pluto. Although Pluto is small, its orbit carries it billions of kilometers beyond Neptune. The Kuiper Belt itself stretches far beyond Pluto's path. Even here, most of the region is empty space, inhabited by scattered frozen worlds separated by enormous distances. It was within this distant region that the spacecraft New Horizons performed its historic flyby of Pluto in 2015 after a journey of nearly 10 years. But the Kuiper Belt is still not the true outer boundary of the solar system. Far beyond it lies a theoretical region known as the Oort cloud, a vast spherical shell of icy debris that may extend halfway to the nearest star. This region is believed to be the source of long-period comets that occasionally fall toward the inner solar system. The Oort cloud, if it exists as predicted, would represent the largest structural component of the solar system by far. When this full scale is considered, the solar system becomes less of a compact family of planets and more of a vast gravitational influence extending across trillions of kilometers of space. The distance from the Sun to the outer edge of the Oort cloud may exceed 1 light-year. This means that the solar system itself occupies a significant fraction of the distance to the nearest stars. When scientists discuss the boundary of the solar system, they often refer to the region where the influence of the Sun's solar wind ends and interstellar space begins. This boundary is called the heliopause. Spacecraft such as Voyager 1 and Voyager 2 have crossed this boundary, becoming the first human-made objects to enter interstellar space. Even reaching this point required more than 40 years of continuous travel. Yet even at this distance, these spacecraft are still only a tiny fraction of a light-year from Earth. Measured on a cosmic scale, the entire history of human exploration has barely left the doorstep of our star system. The true scale of the solar system becomes even more striking when compared to distances between stars. If the orbit of Neptune were represented by a circle, 1 kilometer in radius, the nearest star system would be more than 4,000 kilometers away. In this comparison, the solar system itself would occupy only a tiny dot within a vast interstellar desert. This reality reveals the second great truth of the solar system in scale. It is immense by planetary standards, yet microscopic compared to the distances between stars. The size of the solar system also explains why interstellar travel remains one of the greatest technological challenges humanity has ever faced. Even at the fastest speeds achieved by spacecraft today, reaching the nearest star would require thousands of years. The solar system, though only one small corner of the galaxy, already demands multi-decade missions just to reach its outer boundary. Scale also shapes the behavior of gravity. Close to the Sun, objects orbit quickly and with strong gravitational influence. Farther away, orbital speed slow and gravitational binding weakens. This is why inner planets complete their orbits in months, while outer planets require decades or even centuries to complete a single revolution. The immense size of the solar system also creates natural reservoirs of ancient material. Objects in the outer regions preserve the original chemical conditions that existed when the Sun and planets first formed. These frozen remnants act as time capsules that help scientists reconstruct the earliest history of our planetary neighborhood. Despite the staggering distances, all planets within the solar system share a common origin. They form from the same rotating disk of gas and dust that surrounded the newborn Sun. More than 4.5 billion years ago, gravity slowly pulled matter together, building the rocky worlds close to the Sun and the giant planets farther out where ice and gas could condense. The scale of the solar system shaped the outcome of this process. The inner region became compact and rocky. The outer region became spread out and dominated by gas and ice. Between them lies a long transition zone, marked by vast empty space and scattered debris. When viewed from far beyond, the solar system would not appear as a bright cluster of planets surrounding a star. It would appear as a faint swarm of orbiting material spread across an enormous volume of space, most of it completely empty. The Sun, a living star. The Sun is the central engine of the solar system and the reason life exists on Earth. It is a medium-sized star located at the heart of our planetary neighborhood, providing the light, heat, and energy that drive Earth's climate, oceans, atmosphere, and biological systems. Without the Sun, Earth would be a frozen, lifeless world drifting through space. The Sun formed about 4.6 billion years ago from a collapsing cloud of gas and dust. Gravity pulled this material together until pressure and temperature at the core became high enough to ignite nuclear fusion. From that moment, the sun became a stable, self-sustaining source of energy. Today, it continues to convert hydrogen into helium at a massive scale, releasing enormous amounts of energy every second. At its core, the sun reaches temperatures of about 15 million degrees Celsius. Under these extreme conditions, hydrogen nuclei collide and fuse together, forming helium and releasing energy. According to Einstein's equation E=mc², every second the sun converts about 4 million tons of matter directly into energy. This energy radiates outward through the sun and eventually reaches Earth as sunlight. The sun has a diameter of about 1.39 million kilometers, which is roughly 109 times wider than Earth. It contains more than 99.8% of all the mass in the solar system. If Earth were placed inside the sun, more than 1 million Earths could fit within its volume. Despite this immense size, the sun is considered an average star when compared with many others in the galaxy. The surface of the sun, known as the photosphere, has a temperature of about 5,500 degrees Celsius. Above it lies the chromosphere and the corona, which extend millions of kilometers into space. The corona is surprisingly much hotter than the surface, reaching temperatures of several million degrees. This extreme heat remains an active area of scientific research. The sun is not a solid object. It is a massive sphere of plasma, a state of matter where atoms are stripped of their electrons due to extreme heat. Because of this, the sun does not rotate as a single rigid body. Different parts rotate at different speeds. The equator completes a rotation in about 25 days, while the polar regions rotate more slowly. The sun's energy output is not perfectly constant. It follows an approximately 11-year cycle of activity marked by changes in magnetic behavior. During periods of high activity, dark regions called sunspots appear on the surface. These regions are cooler than their surroundings but are associated with intense magnetic fields. Solar flares and coronal mass ejections occur when magnetic energy suddenly releases from the sun's atmosphere. These explosive events eject charged particles into space at extremely high speeds. When directed toward Earth, these particles interact with Earth's magnetic field and atmosphere, producing auroras near the polar regions. In severe cases, they can disrupt satellites, power grids, communication systems, and navigation networks. Earth is protected from most of this radiation by its magnetic field, but this protection is not perfect. Modern technology has made humanity increasingly sensitive to solar activity. Satellites, astronauts, aviation systems, and electrical infrastructure can all be affected by powerful solar storms. Understanding and predicting solar behavior has therefore become a vital part of space science. The sun's gravity dominates the entire solar system. It holds the planets in their orbits and governs the motion of comets, asteroids, and dust. Even distant objects in the outer regions of the solar system remain bound to the sun's gravitational influence. Without this steady gravitational anchor, the planets would drift into interstellar space. The sun also shapes Earth's climate on geological timescales. Small changes in solar output, combined with Earth's orbital cycles, have contributed to ice ages and warm periods throughout Earth's history. While human activity is the dominant driver of modern climate change, the sun remains the fundamental energy input that makes all climate systems possible. Every biological process on Earth ultimately depends on solar energy. Plants convert sunlight into chemical energy through photosynthesis, forming the base of nearly all food chains. Animals and humans depend on this stored solar energy for survival. Even fossil fuels represent ancient sunlight trapped in organic material over millions of years. The sun also defines time for life on Earth. The rotation of Earth relative to the sun creates the cycle of day and night. Earth's orbit around the sun creates the year. Seasonal changes arise from the tilt of Earth's axis as it moves around the sun. The rhythms of biology, weather, and human civilization are all fundamentally tied to solar motion. Despite its stability, the sun is not eternal. Like all stars, it has a finite lifespan. It is currently about halfway through its main sequence phase, during which it steadily fuses hydrogen into helium. In approximately 5 billion years, the Sun will begin to exhaust its hydrogen fuel. As this happens, it will expand into a red giant, engulfing the inner planets and dramatically altering the structure of the solar system. Earth itself may be destroyed or rendered completely uninhabitable during this process. After its red giant phase, the Sun will shed its outer layers into space, forming a planetary nebula. The remaining core will collapse into a dense white dwarf, slowly cooling over trillions of years. At that point, the Sun will no longer shine as a living star, but will persist as a dark stellar remnant. Despite this distant fate, the Sun today remains remarkably stable. Its energy output changes only slightly over time, allowing life on Earth to persist over billions of years. This long-term stability is one of the key reasons complex life was able to evolve. Human exploration has begun to study the Sun at close range with advanced spacecraft. Missions such as the Parker Solar Probe have flown closer to the Sun than any spacecraft before, passing through the outer layers of its atmosphere to directly study the behavior of solar plasma and magnetic fields. These missions are helping scientists understand how solar winds form and how energy moves through the Sun's outer layers. From Earth's surface, the Sun appears constant and predictable, rising and setting with regular precision. Yet in reality, it is a dynamic, violent, nuclear furnace, producing more energy every second than humanity will use in many generations. The Sun connects Earth directly to the wider universe. It is part of the Milky Way galaxy, orbiting the galactic center once every 225 to 250 million years. As it moves through space, it carries the entire solar system with it. Earth is therefore not only orbiting the Sun, but also traveling through the galaxy at immense speed. The Sun is also one of hundreds of billions of stars in the Milky Way. Many of those stars host their own planetary systems. Some thousands of these distant suns are known to have planets, and many of those planets may exist within habitable zones similar to Earth's. Yet despite this vast cosmic context, the Sun remains uniquely important to us. It is the only star whose surface we can study in detail. It is the only star whose storms can directly affect our technology. It is the only star that directly governs the conditions for every living organism on this planet. Every breath taken by a living being, every movement of wind and water, every cycle of growth and decay traces its energy source back to the Sun. It is not merely a bright object in the sky, it is the engine that makes Earth a living world. The Sun is a living star in the strict physical sense, constantly changing, constantly releasing energy, constantly shaping the space around it. And for as long as it continues to burn, Earth will remain a place where life can exist. Mercury's harsh world. Mercury is the smallest planet in the solar system and the closest one to the Sun. It is a world defined by extremes, shaped by intense heat, brutal cold, violent radiation, and a surface that has remained largely unchanged for billions of years. Among all the planets, Mercury experiences the most dramatic temperature differences and some of the most extreme physical conditions ever observed on a planetary body. Mercury orbits the Sun at an average distance of only 58 million kilometers. At this range, it receives about 7 times more solar radiation than Earth does. Sunlight on Mercury is so strong that the planet's surface temperature during daytime can rise above 430 degrees Celsius, hot enough to melt lead. Yet when night falls, temperatures can plunge below minus 150 degrees Celsius, cold enough to freeze most gases solid. No other planet experiences such violent temperature swings. This extreme behavior is caused by several factors working together. Mercury has almost no atmosphere to trap heat. Unlike Earth, which is buffered by air, oceans, and clouds, Mercury's thin exosphere offers no protection from rapid heating or cooling. When sunlight strikes the surface, heat builds instantly. When darkness arrives, that heat escapes just as quickly into space. As a result, Mercury's day and night sides behave like two different worlds that never balance out. Mercury's position so close to the Sun gives it one of the fastest orbital speeds in the solar system. It completes one orbit around the Sun in only 88 Earth days. However, its rotation on its own axis is extremely slow. One full rotation takes about 59 Earth days. This unusual combination creates a strange phenomenon known as a 3-2 spin-orbit resonance. meaning Mercury rotates 3 times on its axis for every 2 trips around the Sun. Because of this unusual motion, a single day on Mercury, measured from one sunrise to the next, lasts about 176 Earth days. This means any location on Mercury experiences extremely long periods of blazing sunlight, followed by equally long periods of deep freeze. There are no fast transitions between day and night, only slow, relentless shifts between thermal extremes. Mercury's surface closely resembles that of the Moon. It is heavily cratered, covered with impact scars formed over billions of years. These craters record a violent early era when the inner solar system was filled with debris that frequently collided with planetary surfaces. Unlike Earth, which erases most impact marks through erosion, tectonics, and weather, Mercury preserves its scars almost permanently. One of the most striking features on Mercury is the massive Caloris Basin, an impact crater nearly 1,550 kilometers wide. This enormous scar was created by an asteroid impact so powerful that shock waves traveled through the planet and reshaped terrain on the opposite side. The Caloris Basin stands as physical evidence of the scale of destruction that shaped the early solar system. Mercury's interior is as extreme as its surface. The planet possesses an unusually large iron core that makes up about 85% of its radius. This gives Mercury one of the highest densities of any planet, second only to Earth. Scientists believe this oversized core may be the result of a massive ancient collision that stripped away much of Mercury's original rocky mantle, leaving behind a metal-rich remnant. Despite its small size, Mercury has a global magnetic field. This was a major surprise to scientists because magnetic fields are typically generated by large molten planetary cores in motion. Mercury's weak but measurable magnetic field suggests that part of its core remains at least partially molten, even after billions of years of cooling. Mercury's magnetic field interacts directly with the solar wind, creating a compact magnetosphere that is continuously battered by charged particles from the Sun. In some regions, solar particles can directly strike the surface, knocking atoms free and replenishing Mercury's extremely thin exosphere. This constant interaction makes Mercury one of the most space-weathered planets in the solar system. For centuries, Mercury remained poorly understood because it is extremely difficult to observe from Earth. Its proximity to the Sun means it is visible only briefly near sunrise or sunset, always low on the horizon, and often lost in solar glare. Even the most powerful ground-based telescopes struggled to reveal surface details. Real understanding of Mercury began only with robotic exploration. The first spacecraft to visit Mercury was Mariner 10, which performed 3 flybys in the 1970s. It mapped roughly 45% of the planet's surface and revealed a world of craters, cliffs, and ancient lava plains. Much later, the Messenger spacecraft entered orbit around Mercury in 2011 and remained there until 2015. For the first time, scientists were able to study the entire planet in detail over many years. Messenger confirmed many earlier theories and delivered several major surprises. One of the most important discoveries made by Messenger was the presence of water ice in permanently shadowed craters near Mercury's poles. Despite Mercury being the closest planet to the Sun, some regions near its poles never receive direct sunlight, due to the planet's very small axial tilt. These permanently shadowed regions remain at temperatures cold enough to trap water ice for billions of years. Radar observations and neutron measurements confirm that thick deposits of frozen water exist within these dark polar craters, probably delivered by comet impacts over long periods of time. This discovery overturned the idea that Mercury is completely dry and demonstrated that even the harshest environments in the solar system can preserve volatile materials. Mercury's surface is also marked by long curved cliffs known as lobate scarps. These cliffs formed as the planet slowly cooled and shrank over time. As Mercury's interior contracted, the outer crust buckled and fractured, creating massive surface compressions. Some of these cliffs rise more than a kilometer high and stretch for hundreds of kilometers across the landscape. These features provide direct evidence that Mercury is still slowly shrinking as it cools, even after billions of years of geological history. Mercury has no meaningful atmosphere in the traditional sense. Instead, it possesses what scientists call an exosphere, a thin cloud of atoms blasted off the surface by solar radiation and micrometeor impacts. This exosphere consists mainly of oxygen, sodium, hydrogen, helium, and potassium. Because this atmosphere is so thin, it cannot transport heat, sustain weather, or provide protection from radiation. As a result, Mercury's surface is directly exposed to the full force of the sun and the vacuum of space. Any human attempting to stand on Mercury without massive protection would be killed almost instantly by heat, cold, and radiation. Despite these hostile conditions, Mercury plays a crucial role in helping scientists understand how rocky planets form and evolve under extreme solar influence. Because it formed so close to the sun, Mercury experienced temperatures and radiation levels that no other planet did. Studying Mercury allows scientists to test theories about planetary interiors, magnetic fields, and surface chemistry under intense conditions. Mercury also provides insight into the early history of Earth. Billions of years ago, Earth itself experienced far more intense radiation, impact bombardment, and volcanic activity than it does today. Mercury serves as a kind of geological museum, preserving ancient planetary processes that Earth has long since erased. Today, Mercury continues to be studied by international missions such as Bepi Colombo, a joint project between Europe and Japan. This mission is designed to closely examine Mercury's magnetic field, composition, surface evolution, and interior structure with greater precision than ever before. It is expected to unlock new answers about how this extreme planet functions and how it has changed over time. Mercury may not be the largest or most visually dramatic planet in the solar system, but it is among the most scientifically important. Its harsh environment, extreme temperature cycles, and metal-rich structure make it one of the best natural laboratories for understanding how rocky worlds behave close to blazing stars. From the perspective of Earth, Mercury is just a faint moving point near the Sun. From a scientific perspective, it is a world of violent extremes, frozen shadows, solar infernos, and ancient scars written across a metal-heavy landscape. Mercury represents the limit of what a rocky planet can endure. It exists at the boundary between solid planetary worlds and the intense furnace of a nearby star. It shows how close a planet can exist to a star and still survive as a distinct body.